Okay. Hello, everyone. So today, we're going to be continuing on a discussion that I started at last year's ETHCC, where I gave this talk on resource pricing. I kind of broke down how certain blockchains, such as Bitcoin and Ethereum, price their various orthogonal resources. Since then, we've all become about 12 months wiser. Some of us have gained also about 12 pounds. But we are now at the next ETHCC, and we're going to talk about resource pricing yet again. This is, again, part 2 of this conversation. So we're going to start off by talking about plastic grocery bags, plastic shopping bags. And I swear this is going to go somewhere, so don't immediately dismiss this as being orthogonal to the conversation. This will go somewhere. So about in 2008, some cities in Canada implemented a rule where you would have to pay 5 cents if you wanted to get a plastic shopping bag when you went grocery shopping, for each bag. Prior to this, grocery stores just handed them out as freely, essentially, just completely freely. You know, if you wanted to pass a plastic grocery bag to carry your groceries, they would just give it to you. Fun story, that rule was actually repealed, but regardless, the point being it was implemented in the first place, to curb various things. One was waste, right? Dealing with these plastic bags in the landfill wasn't exactly very good or easy. It was also for environmental reasons, right? The environmental effects, long-term environmental effects of plastic and things like fossil fuel consumption and so on can be pretty detrimental to the environment. So they implemented this rule that if you want to get a plastic bag when you go buy your groceries, you have to pay 5 cents. That's it, just a measly 5 cents. And in a few years, this dropped the usage of plastic bags in grocery stores by up to 70%. So it's a pretty astounding result given how small this change was. So what are some lessons we can get from this? I said this is going somewhere. So in a completely free market, there are two parties. There's producers and there's consumers. In other words, there's supply and demand. And where the two meet, you get some sort of price equilibrium, a price for a good or a service, or a resource, if you will. But we don't live in a free market, do we? Because there's a third party. There's literally everyone else on the planet, right? When it comes to things like, let's say, a single-use plastic, when it comes to things like, you live next to a coal plant, so the emissions from a coal plant, the consumption of fossil fuels, you don't just have a producer and a consumer, you also have literally everyone else on the planet. And you have the planet itself that is also going to be affected by this, by this transaction. And the kind of lesson in this is that the free market, where you only have two parties, the consumer and the producer and the consumer, is not very good at pricing in and accounting for negative externalities. An example of this is exactly like we saw with the plastic bags, the environmental waste caused by single-use plastics. If you have, coal power plant, this is like the trivial examples you can see anywhere. There's obviously much more nuanced things, but the trivial examples is like the coal power plant. If you live nearby it, you see the emissions. The beer can the 6-packs, those little plastic rings can go and like choke turtles, sea turtles, right? These are negative externalities that are not actually involved directly in the transaction that takes place, and the free market doesn't actually account for these things. If it did, then the resource might be more expensive to purchase, such as plastic bags going from free to not free to 5 cents. So what is good at, or what is a possibility to actually account for negative externalities? That is the thing known as regulation, which is something that in the blockchain space we don't really like talking about because it has certain negative connotations, but you kind of do need regulation if you want to price in and account for negative externalities, which do exist in the blockchain space. And believe it or not, this talk will not be about proof of work at all and its energy consumption. So how does what we discussed relate to the blockchain? So in any blockchain, be it Bitcoin or Ethereum, whatever you have, there is a resource that is being sold. There's a resource that is available to purchase, and that resource is block space. In Ethereum, block space is measured in gas, right? It's a resource. Now, from my talk last year, and kind of briefly summarizing it, you don't actually just have a single resource, gas. I mean, that's what Ethereum provides. But really, under the hood, what a blockchain provides is a number of orthogonal resources, such as a computer's CPU time, power consumption, running computation stuff actually consumes power, network bandwidth, memory usage and capacity, memory I/O potentially, and also disk usage for things like storing the blockchain state. Blockchain state being things like account balances, contract storage slots, and whatnot. All of these things are actually orthogonal resources. They're not all just one thing in gas, but they're priced in gas in the Ethereum chain. So the supply of these orthogonal resources, like the maximum supply that is provided by the blockchain, because again, we're here analyzing supply and demand stuff, is what is it bounded by, right? It's not actually a free market. It is not the case that if people want more block space, that the blockchain will provide more block space to keep the price at an equilibrium. The fee market that we all know and love when it's a bull market and Ethereum fees go up to $100 is actually caused by not having a free market on the capacity of gas. The capacity of gas, or the capacity of resource consumption really, is bounded, it's fixed, it's set through what we could call regulation. Right? The protocol itself enforces some regulation. It does not allow a free market on the gas capacity, on the block space of the Ethereum chain. Rather, we enforce and we say, you can only have 15 million gas per 12, 13 seconds. Right? That is a form of a regulation. That's how we kind of bound upper capacity. This is obviously needed because if you allow the block space to be completely unconstrained, it would be impossible to run a full node, and then goodbye decentralization. OK, so let's see how now Bitcoin accounts for negative externalities and so on using regulation, which is kind of the ultimate irony given the given the libertarian roots of cryptocurrencies, crypto anarchist and all this other stuff. It's kind of ironic that Bitcoin has regulations built into its protocol around resource pricing. So last year I discussed SegWit a lot, so if anyone wants to learn more, I suggest you refer to that talk. But to give a very brief overview, the SegWit protocol change that was done in around 2017 or so, the Bitcoin block size wars, was essentially the separation of witness data from non-witness data, where witness data is something like a digital signature. In other words, it's authorizing some state change. And the non-witness data is a state change. It's like state changing data. Things like, Alice sends 5 Bitcoin to Bob. That's the non-witness data. And the witness data is Alice's signature that she authorizes the spend. The reason you want this separation between these two things is that the signature, once you've validated it, once you've executed, once you've actually verified the signature against the state transition, you don't actually need to keep it around in your full node. Right? Your full node can actually discard witness data, but your full node needs to keep around witness data, or it can discard witness data, but it needs to keep non-witness data. In other words, it needs to keep the account balances of everyone, right? If you don't know the account balance, if you don't know Alice's account balance, you don't know if Alice has 5 coins to send to Bob. So your full node needs to keep what is called state around forever. And the state is a negative externality. So what are the regulations in Bitcoin around this negative externality? Here's some brief clips from Peter Wulle, one of the Bitcoin core developers, a former maintainer of Bitcoin Core. He's talking, the kind of background on these tweets is that witness data actually has a 4x discount in costs over non-witness data. So 1 byte of witness data 4 bytes of witness data costs as much as 1 byte of non-witness data. which may seem like, well, why are you doing this price fixing, right? Why is witness data 4 times cheaper? Why don't you just make them the same price if they're both bytes? Right? This seems a bit unfair to charge witness data less. And that's because just bytes themselves aren't actually a good measure of the negative externalities imposed by that byte. Because witness data can be discarded, therefore there's no negative externality to that byte. You download it, you execute it, and then you discard it. Non-witness data, in other words, state-changing data, you need to keep that around forever. So it's not just you download that byte, you execute it and discard it. You have to download it, execute it, and keep it forever, potentially. That keeping it forever, that uses up disk space. That is a negative externality that all full nodes need to pay for forever, and you have to account for it in some way. And that's what Bitcoin does. It makes witness data cheaper than non-witness data, or rather, it makes non-witness data more expensive than witness data. OK, how does Ethereum do it, right? This is probably more familiar to you, and it's a much more kind of nuanced and detailed thing than just bytes and witness and non-witness data. There's a gas accounting schedule, right? Every instruction in the Ethereum virtual machine has a particular cost in gas associated with it, right? So an addition might cost 2, 3 gas, right? A state-changing operation like a state read might cost several hundred gas. I think nowadays, I don't remember when I took the screenshot, nowadays a state read I think might cost a couple thousand gas if it's a cold read. And a state write costs 20,000 gas, right? So there's an almost 10,000x difference between a state write and an addition. And why is this the way it is? Why isn't it something different? And what is this ultimately? Is this a free market? Well, it's saying that a state write costs 20,000 and an addition costs 3. That ratio between them is fixed. In other words, it's not actually a free market between your different resources. It's actually regulation. So anything you do with resource pricing, this accounting, this differentiating of different resources, which again, you don't just have one resource, you have multiple orthogonal resources, and you have negative externalities. Accounting for these negative externalities is ultimately a form of regulation, and it's a regulation enforced by the protocol itself. So we talked a lot about supply here, but we haven't talked about the other side of the coin, right? We've talked about supply, we talked about how to add some regulation to that supply, but we haven't talked about the other side, which is the zoomer over here, the consumer, right? What can we do with these guys? So as we saw before, in a free market, you have supply and demand, and where they meet, there's going to be some price equilibrium. Now, you would expect that in a free market, if you increase the available supply and the demand does not change, then the price will decrease, right? There's just more of the stuff. But if the price has some sort of equilibrium and the demand is flexible rather than inflexible, then if you increase the supply, the demand can also increase, and you can keep the price the same, right? This isn't exactly a particularly interesting thing for us if our blockchain resources are all metered under a single thing. In other words, if all you have is bytes, or if all you have is gas, this notion that you can potentially change the supply to then affect the demand and keep the price the same isn't particularly interesting because, as we saw way back in the previous slides, you can't change the supply of block space, really, right? The supply of block space is fixed for any blockchain. Ethereum is 15 million gas every 13 seconds. Bitcoin is 4 megabytes every 10 minutes, right? BSC is whatever it is, right? There's some sort of fixed capacity on the block space that every blockchain provides, and you can't increase it flexibly, right? So the block space is not flexible. But what can we do? We remember that the block space isn't actually a homogeneous single resource that is not just gas. It's something else, right? Is that the resources that a blockchain provides are fundamentally backed by real computer hardware, right? There is a real CPU, there is real power consumption, there's real network bandwidth, there's real physical RAM, then there's real disk usage used to store the state. And these things are what the blockchain network provides, right? It's an abstraction, it's a virtualization over real hardware to create the internet computer, right? So it doesn't just have a single resource, it actually has multiple resources that are orthogonal, and you can actually use one resource more and you can use one resource less. Now, out of these, some of these are negative externalities and some of them are not. Right? CPU usage, for instance, well, first of all, CPUs improve dramatically year over year. Maybe not in single core performance, but in multi-core performance, they improve just, well, I mean, Moore's law is still in effect, right? Despite everyone's prediction that it'll end someday, it's still in effect even to this day. The CPUs are getting dramatically faster. What is not necessarily getting better is potentially things like power consumption. Right? You don't necessarily want your blockchain to have a lot of power consumption when it verifies transactions. Again, this is not related to proof of work, but rather just the node execution. Things like bandwidth, for instance, network bandwidth. You download your block once, and then okay, you're done. Right? You don't have to re-download it again. You don't have to infinitely consume network bandwidth for all future time for that one block you've downloaded. Similar thing for RAM. But disk, on the other hand, disk is where you're going to store your blockchain state, right? And as we discussed earlier, a blockchain state is things like account balances, contract storage. For Bitcoin, it would be the UTXO set. Those things need to be kept around by all full nodes forever. You can't discard the state because if a full node doesn't know what everyone's balance is, it can't actually verify that a transaction is valid. So this disk usage for blockchain state is a negative externality. When you send a transaction, you can't just pay for the CPU time. You also have to account for, in some way, for the negative externality of this persistent disk usage forever to store the blockchain state. And this can't be done well with the free market, as we've seen. But it can be done through regulation, and it can be done through the gas accounting schedule that we saw earlier, right? You price something like a state right, 20,000 gas, you make it much more expensive than an addition in the hopes that you're accounting for the negative externality. That's why you get that ratio and not a free market ratio between the two. So since we set the ratio, is there anything stopping us from setting the ratio differently? And the answer is actually no. And this is where the graph that we saw in the previous slide here comes in, right? That if you increase supply and price remains the same, then you can also increase demand, right? And vice versa. So what you can do with this is, sure, you can't change the total gas capacity, but what you can do is play around with, through changing the regulations and in anticipation of negative externalities, such as disk usage for state, you can actually make one resource be used more than the other. For instance, if you took the Ethereum gas accounting schedule and you said, let us make the cost of writing to storage 10 times more expensive, what would people do? They would write contracts that did something like this. Your blockchain would then use storage less as people were induced, as demand were induced to use storage less. But the total gas capacity is the same, so what would they do instead? Well, they would use more CPU. And that is what you want. You don't want negative externalities. You want to reduce those as much as possible. So you want to reduce state usage, and you want to encourage things that are just one-time costs, such as CPU time, especially if those one-time costs, if the capacity of those resources that your cost is denominated in can scale greatly year over year, which CPU time does. So you have this very interesting property that we don't actually have to take the gas accounting schedule and just live with it. We can actually induce demand for different orthogonal resources by changing the regulation, by changing that gas accounting schedule. For example, like I said, greatly increasing the cost of S&S storage, right? And encouraging people to use CPU more. And you don't actually have to be reactive with this. A lot of changes, a lot of proposals rather, in the Ethereum ecosystem have said, well, it's more expensive to do storage now than it was a year ago. Why don't we double the cost of storage? But you don't have to be reactive. You can always be proactive. We know where the negative externalities are. It's in state storage. So why don't you be proactive and induce a change in demand by changing the supply, and specifically by changing the ratios in the supply for these different orthogonal resources. OK, so with that, we can wrap up with question time. We have a few minutes. And if anyone wants to follow along with the work that we're doing, here's a QR code for our website. OK, thanks so much, everyone.